for joining this talk. We are going to talk about how we incorporate formal methods into developing tools for Erlang and Erlang-like languages in the BEAM ecosystem. My name is Dániel. My co-presenter is Péter. We are going to talk in two parts. In the first part, I'm going to give you an introduction, and in the second part, Péter is going to deep dive into some technical details. So we are both teaching and researching at University, and in the past few years, we spent serious effort into defining Core Erlang, like the core language of Erlang, in a fully formal manner. So part one is about introduction. I'd like to raise your awareness about using formal methods, formal definitions, and show you like the blueprint of some applications that we can build with formal methods. So let me warm you up before we get into details. So this is a seemingly simple snippet written in Erlang. Let's suppose that A or B are arbitrary values. Okay, so these are variables. They represent values, not expressions yet. So I invite you to think about how you would explain the behavior of this code to someone who doesn't know Erlang or doesn't know how BEAM-like languages work. So this is a case distinction, as you would say, and you have two branches, true or false. And I would say A can be either true or false. So if A is true, then you go for the first branch, evaluate B, and then you get you yield that result. If A is not true, it's false, then you go for the second branch and you yield false. Of course, you, sitting in the audience and trying to stay with me, you have this idea that I claimed that A can be true or false, which is far, far from the truth. We are talking about a language that is dynamically typed. So we don't know in advance whether A is a Boolean or it's of any other type. So what happens if A is not a Boolean? You get an error. You get an exception saying there were no matching case clauses, something like that. All right. So if you had to explain the behavior of this, you would also incorporate this aspect, right? Okay, so let me just slightly change this example. Instead of the case, let's have an if. The behavior is still the same. So it's like a lazy conjunction. If A is true, you go for the value of B. Is A false, then the second branch is going to be selected and you yield false. What happens if A is not a Boolean value? You get, sorry, it's gonna be false. So you are going to fall to the second branch because any value other than true is going to be regarded as false. So as a guard, if you have a number as a guard, it's going to be regarded as false. So you're going to go to the second branch. So I would say, in some sense, you could conclude that these two snippets are not behaving the same way. Péter is going to talk more about that. All right. So we are trying to explain, we're trying to reason about how these snippets behave. And I think there are basically two approaches to, among the audience or among the programmers, how we would argue about the behavior of code. I think the default one is that we know this language has an implementation, and we can take any of these expressions and set a concrete A and concrete B, and then evaluate, and we will inspect what happens. So we gain an understanding about the behavior of the software by just running it. You can execute it, and you can test it, right? Well, some of us would actually favor going for language documentation or language specification. And rather than just trying to run it on multiple values, what if we could deduce from the documentation what is supposed to happen? What is the expected behavior? So as you can imagine, if you fire up your Erlang interpreter and you set A to true and B to true, you get true. if A is false, B is true, you get false. What if A is a number? Well, as we discussed, it is going to be regarded as a false, so you fall for the second branch. And even though in C-like languages, any number that's positive would be regarded as true, that's not the case here. It's still false. The problem with this argument that I have on my slide is that there could be infinitely many other cases. So I am actually worried that I cannot conclude yet whether for any other value the expression is going to be false. I have an idea that it should be the case, so I could test it with 2, 3, 4, 5, 6, and so on, but this is just an idea, it's not justified. So maybe an alternative approach to explaining what happens is that I go for this specification of the language where someone explained exactly what is supposed to happen. This is not the implementation of the language, this is the specification of the language. And it says, an if expression is scanned sequentially until a guard sequence evaluates the true. Okay, now we are closer to the truth. What is a guard sequence and what does it mean to evaluate the true? Well, you are going to have guard expressions in a guard sequence, and the guard sequence is true if at least one of the guards is true. Great, so we have to know what a guard expression is and how it works. Actually, it's an expression that can evaluate to, it's restricted, but it evaluates to a value, and if the value is true, then you regard it as true, otherwise you regard it as false. Actually, in an older version of the documentation, it is explicitly said that any other constant other than true is going to be regarded as false. So now we have a very good understanding about this seemingly simple snippet without running the code. We deduced what it is supposed to do from the specification. So is this a better approach? Well, I think testing has its role. So it is great that we can inspect the behavior by executing programs, but it is, in some sense, it is restricted. With testing, we can never ensure that there are no errors. Whereas if we use the language specification or the documentation, what we do is explain the behavior. Rather than inspecting it in various cases, we explain, we deduce. So I would say that the first approach is testing, and the second approach would be named reasoning. So when you have a concrete program and a concrete input, you can test it. But if you don't, so maybe your program is parametric, maybe it's symbolic in its inputs, you can still use the specification to do reasoning. Yeah, great. So can we do the reasoning formally? Well, not yet, because the documentation is written in English, typically. It's a large English document, especially for languages, old languages like C, C++. You open the language specs and it's going to be hundreds of pages. So you can take the documentation, but for reasoning, you need something more rigorous, more unambiguous. And here comes formal methods. So if you think about the program or the programming language as a mathematical definition, then you use formal logic to do reasoning. And this is what we are trying to advertise here, that we are very passionate about this. And this is something that today is now in reach and scalable. So you turn your language documentation into a mathematical definition, and then you can turn your natural English reasoning into a formal proof. It's still a question who's going to check your proofs, because maybe you are human, you are writing proofs, but you make mistakes. If you do it on paper, you are very likely to make mistakes. You need other humans to catch your errors. Well, you can do this whole thing in a so-called formal proof assistant. You may have heard about proof assistants like Rocq, Isabelle, Lean. These are formal mathematics, and they allow you to write proofs that are machine checked. So you cannot make mistakes in your proofs. Okay, so we have to turn this English documentation into a mathematical definition, and then we get an alternative a mathematical implementation of the language. So is it superior to any other implementations? Well, in some sense, yes, because it's going to be general, it's target independent, it's rigorous because it's mathematical language, and it allows you to do formal reasoning using a formal logic. But of course, it's made for reasoning and not for execution. So typically, it's going to be very slow. It is extensive, complex, and it requires expertise to work with. So, well, I would argue that if you want to do reasoning, you need this tool, but maybe not all of us are going to write proofs in the following years using the formal semantics definition. But that's not a problem, because formal semantics is not the tool. It enables something. It provides you an infrastructure for building trustworthy tools. So what our message with this presentation is that we are not trying to enforce you to learn formal methods and use our tools as they are. What we are suggesting here is that maybe together we can build tools on top of on this formal foundation that people can actually use. What kind of tools do we have in mind? For example, you can take your formal definition in any style you may have in formal means, and you can turn it into an executable version. We actually did that with our definition, and we synthesized an interpreter for Erlang based on the formal definition of Core Erlang. Is it fast? Of course not. There are no optimisations taking place. This is slow as hell, but it's special because when you run a program, you evaluate an expression using this implementation, you generate a proof about the correctness of the result that you get. Actually, it explains to you how the result follows from the language specification, which is amazing, I think. This work is supported by EF, and it was presented at this year's Erlang workshop. We are very proud of that. A similar work that we started doing is symbolic execution, also on top of the formal definition. You can do that. So the formal definition doesn't need the concrete values. It doesn't need all these concrete parts. It can understand the program symbolically. So you can explore the execution paths and maybe take the computation tree and somehow merge it into a graph and show it to the programmers so that they can better understand what are the various execution paths that their programs can take, also supported by EF. And another branch of development that we are doing, we are very enthusiastic about static analysis. And there are many tools out there that do linting static analysis, and they do, for example, they can locate some security vulnerabilities in your programs, such as auto-execution. Now, if you have such a tool, if you ever use such a tool, you know that they approximate programs' behavior, and sometimes they produce false positives. Now, when you have a false positive, what you do is try to exploit. Well, you get a hit, and you want to decide whether it's a true or false positive. What you do is try to exploit the problem. Well, you don't have to try. The formal semantics knows exactly whether the program exists or not, and it can prove it. And also, we are working on a tool for somehow making a natural combination of testing and verification based on SMT solving. Our long-term goal is to take quick check properties, and for the simple ones, rather than testing the program, we will do the verification on top of the formal semantics. This work is also supported by the EF. But I can tell you that by far the most impactful applications of the formal semantics is that formal semantics allows you to reason about programs' behavior and also about whether two programs are equivalent. And this leads me back to the running example where we had this if and case and are argued that they are not equivalent. That could be understood as a refactoring step, and maybe could be understood as an optimization step if it was a lower level. And if you want to reason about whether optimizations and refactorings work properly, well, you need to prove semantic equivalence. So more on this from Péter.
Thank you. Are you warmed up? Because now what we are going to do is we open the bonnet and check what's inside. And unfortunately, what you find is mathematics. So let's just get a very brief peek there. Actually, you not only find mathematics in our case, but also a language called Core Erlang. Do you know Core Erlang? Have you heard of it? Some of you have, some of you maybe did not. Core Erlang is essentially an intermediate language used in the Erlang compilation pipeline by the standard compiler. And actually, not only that, but also other Beam-based languages can be translated or compiled to Core Erlang. Why is this important? Because if you suppose that the compiler of these languages is trusted, then you can exploit results about Core Erlang to indirectly reason about your Gleam programs, for example. Suppose that you want to prove that your Gleam program is correct, then you can translate it by the compiler to Core Erlang, prove the correctness there, and you can say that the program is correct, supposing that the Gleam compiler works correctly. All right. What is Core Erlang? You can think of Core Erlang as essentially a desugared, restricted version of Erlang. For example, here was this small snippet shown to you by Danny, and this translates to Core Erlang to this case expression without any optimizations. And as you can see, the variable a explicitly became a guard from the if. It became an equality check between the variable a and true. And the compiler also generated a third case, which is used when none of the previous clauses can be matched. Obviously, in this case, we can never reach that clause, and if you turn on the optimization in a compiler, this clause will be eliminated. And actually, this is also a step for which we could use formal reasoning to verify that eliminating such a clause in a program is behavior preserving. There was another reason why we chose Core Erlang to investigate in our project. It has a very well-established language specification document. But there is one issue with this page, and that's the date of it. It's quite old, and since 2000, a number of EEPs affected Core Erlang's syntax and semantics too. So what we did is when we expressed Core Erlang in a mathematical sense, we not only took this specification, but also checked the implementation of Erlang and based the semantics on these two main sources and related researches. So Dániel already told you what is a formal semantics. It's basically a mathematical definition of a programming language. In our case, what we have is a so-called small step semantics, which you can imagine as a relation which describes how expressions evaluate in a step-by-step manner. Let's check a concrete example. Suppose that you have this two-element list. Actually, this is the syntax in Core Erlang for function, for built-in function calls. So you have a three-element list. How do you evaluate it? Well, obviously from the back, right? Because that makes sense. This is just how Core Erlang works. We thoroughly checked this issue, and this is what we found. So first, the last part of the list, this empty list, will be evaluated. You extract it, and since it is already in a normal form, it's already a value, you can evaluate it to itself and put it back into the list. Well, nothing really changed at this point. You can take the next expression, you can evaluate it to 5, and then put it back into the second place. You get 5 there, and then you take the first expression, evaluate it to 3, and put it back, and what you get is a two-element list. So the final result is 3, 5, an empty list. I omitted a lot of details here because I didn't explicitly explain how these call expressions evaluate. actually, what defines how these these expressions evaluate is a mathematical relation. But actually, the entire relation can fit into this slide. So we have a bunch of formulas and some more and some more and some more. So when Dani said that it requires expertise to work with, he meant that. And okay, this is kind of fitting the slide. And this is only the sequential fragment of the language. And we have also expressed the semantics of a concurrent subset of Core Erlang. And those who might be familiar with the concurrent part, you would say that this is where the fun begins, where interesting behaviors happen. But this talk will not be focused on that. But if you are interested, just feel free to approach us in the breaks. We are really glad to talk about this. So, right, we have a formal semantics on paper. But yeah, that's precise already. But still, if you want to use it, you have to employ manual labor. You need to write your proofs on paper, and others need to check your proofs. And humans are fallible, so you can make errors in your reasoning, and maybe your readers don't notice that. We can do better, and we can express the formal definitions in a so-called proof assistant. What we use in this project is called the Rocq proof assistant. Formerly, it was known as Coq, but it was rebranded this year. And this is a major effort because the proof assistant basically ties your hand, and you have to be explicit about everything. Every tiny sub-proof, every tiny sub-goal has to be proved. But on the other hand, what you get is, well, Rocq is a functional programming language. I could compare it to Haskell maybe. So it's typed, and you can use it to evaluate your definitions. When you are writing proofs, you get guidance from the machine. It will show you your goals, what you need to prove. It will show you the list of hypotheses that are available. So proving is interactive. And all of the proof steps are checked by the machine, and it doesn't give you room for error. It doesn't allow you to make false steps in the reasoning. And when the proof is completed, it rechecks again, looking for errors. All right. So we have expressed the formal semantics of Core Erlang not just on paper, but also in Rocq. And actually, it has an open source implementation, so you can check this on GitHub if you look for Core Erlang and formalization. These are the keywords. So let's move away again from mathematics and go back to our running example. We have these two snippets, which were shown you by Dani. Do you think that these are equivalent based on the presentation up to now? What's equivalence? It's, well, informal, it's something like they behave the same way. Do you think that these are equivalent? Not really, yeah. Some of you are doing this movement. So they are not equivalent. You just discussed that if A is not a Boolean atom, then the first case will be false, and if you evaluate the second expression, it will be an exception. But hang on a minute, these are Erlang expressions, not Core Erlang expressions, and I just presented you a semantics for Core Erlang. What we mean by equivalence here is this. We take these Erlang expressions, use the standard compiler, translate them to Core Erlang, and check the equivalence there. This step is basically what I told you when I was talking about trusted compilation. We trust the Erlang compiler, and when we can prove the equivalence of the corresponding Core Erlang codes, you can infer the equivalence of the original Erlang codes. Obviously, in this case, what we want to prove is the inequivalence, because we just discussed that they shouldn't be equivalent. All right, but we didn't really define what equivalence is. So let me show you a last piece of mathematics. What is program equivalence? I said that basically that means the two expressions behave the same way. By behavior, let's just use this down arrow symbol. If you're interested about more details about this symbol, then just ask us after the talk. I'm really happy to talk about it. And it has a simpler definition than you might think. So these expressions should produce the same behavior, but not in themselves, but in all possible syntactical contexts. What does that mean? Well, if we take our original two codes, they must behave, the entire code should behave the same way if you put a huge context around them for any context, all of the possible contexts. For example, they can occur in a function inside a module. And since we want to prove that these are inequivalent, you just have to show a context where they behave differently. For example, in this case, you can bind A to something which is not true and false, and you will get a difference in the behavior. Therefore, these codes are not equivalent. And actually proving inequivalence with this notion is very simple. You just have to show a context where they behave differently. But if you want to prove equivalence, then you will have a hard time. So what we did here, we developed alternative equivalence notions and to derive this kind of equivalence and prove that they coincide. This took a lot of effort in our project. So getting back to the codes, we can fix this formula. We can prove the equivalence of these two snippets if we eliminate the false pattern and use a wildcard there. And we have a formal proof of such an equivalence. Why is this good for you? Well, why is this applicable? Let me generalize this a bit. Actually, it does not really matter that in the first clause you have B as the evaluable expression. It doesn't matter whether you have false in the second clause. You can generalize it to be any kind of expressions, even the D2. This equivalence will hold for all possible Erlang expressions, even the D2. You can substitute them with everything. And actually, since we proved the equivalence, if you replace these codes inside a bigger code base, due to the contextual equivalence, the bigger code base will behave the same way. So what you have is a proven correct refactoring. You can replace the case expression with the if expression without affecting the behavior in all possible code bases, and vice versa. You can replace the if expression with the case expression. Actually, in the previous talk, Brujo also shown you a lot of, basically a lot of his examples were like refactorings. So those could also be checked by the formal semantics. All right. So these are proven correct refactorings. This is not the only example which we have. We proved a lot of other refactorings, including some concurrent ones, in which case the equivalence becomes much more difficult. Do you know other tools that behave the same way as refactorings? Do you know other tools that take a piece of code and replace parts of it, potentially with simpler ones? Do you know what behaves like that? And potentially all of you have used it. Optimisations and compilers. For example, the Erlang compiler. You can compile an Erlang module with the time option, and it will tell you what compiler passes goes through what are the compiler passes that you will do for your code. And I would like to draw attention to this one, which is called syscore fold. This compiler pass is responsible for an optimization called constant folding. And this is a compiler pass which happens in Core Erlang. So you already took your Erlang code, translated to Core Erlang with the compiler, and one of the steps now does this constant folding optimization. And if you're interested, you can check out its code because it's open source. You go to the GitHub page of Erlang OTP and look for, in the compiler, you look for syscore fold error. And I would like to draw attention to this piece of code here. Let's digest it in a bit more details. So first of all, in the list of parameters, you have a csec. That's also what is called as a do expression in Core Erlang. It's basically a sequence of in sequence evaluating two expressions. it would be an Erlang alternative to just separate the two expressions with a comma. So this is the expression you want to optimize. What it does, first it optimizes in an indirect recursive call, it optimizes the two expressions, and then it will check whether the first expression will fail, because if it does, then it produces an exception, and we don't need to evaluate the second expression. Otherwise, it checks whether the first expression produces a value and doesn't produce any side effects, because if so, in a sequence it doesn't matter that you evaluated the first expression, because the result will be based only on the second expression. So in this case, you can return B1. And if none of the checks pass, then you can just optimize the two expressions of the sequence and recompose the sequence. And here is a small spoiler alert. There is a last part of this optimization we didn't investigate, but we formalized the rest of it with the formal semantics, and we proved that this optimization is correct. So the expression before the optimization and after the optimization are equivalent with the notion of equivalence I showed you before. It only took about 2 weeks of work and a lot of Rocq code, and obviously the semantics, which we built for 7 years. And 2 major helper lemmas, which are quite natural if you think of it. So we formalize this will fail predicate, and if it returns true for some expression, then we prove that this expression indeed evaluates an exception. And the other one is the second one is about the other predicate, which when returns true, then this expression indeed evaluates to a single value without producing any side effects. And based on that, we managed to compose the proof of this simple case in a bigger optimization. And this can be seen as a tiny step towards a more trustworthy Erlang compiler. So, as a conclusion, I would like to highlight a few takeaways from this talk. One takeaway is that there is an open source formalization of Core Erlang, which is implemented in a proof assistant called Rocq. But since it requires expertise to work with, it's not for everyone. But it can serve as the infrastructure to for building trustworthy tools. And we have shown you some examples. For example, there was the reference interpreter to evaluate Erlang programs. We formalized the atom exhaustion vulnerability. And I showed you some applications where we can use verification of program equivalence for refactorings and for compiler optimizations. What we plan in the future is to broaden this scope. We would like to prove further refactorings correct and further compiler optimizations. And our long-term dream is to develop a fully verified compiler for Erlang. And that concludes the talk. Thanks for the attention.
Questions? In the back?
In your formalization, have you modeled recursive types?
The question was, in your formalization, have you modeled recursive types?
Yes, great question. We didn't model types at all. We just formalized the behavior, but no type systems. Yet, at least.
So the semantics of Erlang can be pretty intricate. If you were allowed to kick out one language construct, that's causing trouble.
Let me ask a return question. From Core Erlang or from Erlang? Or both? Okay. Maybe what I would do instead is I would reintroduce receives to Core Erlang, because Core Erlang doesn't have a receive expression anymore since OTP 23. And reasoning about the receive expression is much more simpler than reasoning about the primitive operations on which now receive of Erlang is expressed in Core Erlang. So that would be a simplification in the semantics. Yeah. And potentially, what's also most troublesome is recursion.
For these specifications, do you have any way of knowing that they actually cover the entire language?
Well, we know that it doesn't, but the long-term goal is to have as high coverage as possible. Actually, once we had the concurrent part in Core Erlang, that was a major effort and a major accomplishment. And I think it's from this point on, we usually say that everything we have is representative, and it would require labor to extend it to the full language. So once somebody steps on the stage and says, "I'm going to financially support your work to do that," we are ready to do that.
Dynamic calling of modules. So that's like module, name, and then it calls functions as variables. Do you cover this? And that's challenging?
I think, well, we didn't formalize this behavior in Core Erlang, but I think it's not even appearing in Core Erlang, maybe. I'm not completely sure. But we didn't cover it yet, if so.
But it probably like desugars to some apply calls.
Yes, or like core calls.
Or call calls, which you can handle. Yeah, it is very likely that whatever that comes from Erlang like that is going to be Core Erlang that we can handle.
It would become the same as an apply.
It would be?
It would be the same as an apply.
Okay.
Doing apply with a module.
Yeah, that was my, yeah. Thank you.
For the stream, Robert said it would be the same as an apply. Speaking of the module invocation. I've got a question. So we're talking, maybe about the pros and cons between Erlang and Core Erlang. Are there any things you would want from a lower abstraction pulled in? There are various simplifications and optimisations at the kernel Erlang level, maybe something a lot of people haven't heard about, but any concepts from that direction, lambda lifting, those sorts of things?
So I think not yet, but it's a dream of us to formalize a verified compiler, as I told, and this, what we planned is to formalize kernel Erlang, Beam, and Erlang too. So all of the intermediate languages.
Full spectrum from Erlang to Beam.
Yes.
Because we know that it's possible and it would be a major achievement. And we have a ground application under review for that. And if that succeeded, that would be a very important support to doing this. So we are really waiting for a positive reply from the evaluation committee on that.
Thank you.
We are eager to go down to lower levels and do verification on those levels.
We'll just have to ask the compiler team to not add another intermediate representation.
We are going to formalize it as well.
Anyone else? All right, thank you.
Thank you very much.
Thank you.